Hello all. I'm audible.
Yes, audible.
Yes, sir. Audible.
Good evening.
Good evening, sir.
Good evening, sir.
Good evening. All right. So today we'll be discussing. We'll be having the first PYQ session for the upcoming term on Sunday. So let's get started. We'll be discussing. These are questions from way back, but I think I thought we should start with this. This is from the second term of 2023. No, third of 22. Yeah. So mix of questions from the different concepts from across the 12 weeks. Let's start.
So you are not audible. Are you
Yeah.
speaking?
Yeah, I just started up a Jamboard. I'll be keeping that handy for any
Okay.
calculations or demonstrations. Yeah. So let's see. All right. So which of the following estimators are more likely to be preferred for bagging? So just recapping, this is from ensemble methods, okay? Bagging, random forest boosting. So I hope bagging doesn't need a refresher. Creating synthetic data sets, right? So sampling with replacement from the original data set to create these synthetic data sets, and then training different models, like basically different instances of the same model on these different bags or different synthetic data sets, and then averaging the predictions from all these individual learners. So any would anybody like to opt? Would you like to write in the comments what the answer might be? So decision stump is a decision tree with a single question. Uh, the rest, I believe, yes. Any inputs? So decision stump, decision tree, KNN. This is, by the way, a multiple select question. BNC. Yeah. So why is it BNC? It's because there's a decision stump, right? So this is not like how to say. We want full-fledged, yes, overfit VPNs. So a decision stump will not overfit. So decision tree, if we let the depth of the tree grow unrestricted, then it overfits. Right? So decision tree will not overfit. Right? Decision stump will not overfit, but a decision tree will overfit. A KNN classifier will overfit, and basically, if we had a single learner, then we wouldn't want it to overfit. And so if this wasn't bagging, if you were training a single tree or a single KNN, then we wouldn't want it to overfit. Right? But we are training like an ensemble or like a group of these learners. So what happens is that because they're trained on different bags, so just briefly recapping. Right? So if you have a data set and you're sampling with replacement from the data set, that data set is, if it's big enough, it's like a proxy for the population. So if you're sampling with replacement from the original data set, that is as close as you get to sampling from the population. So these synthetic data sets that you create, these bags, right? They are as close as you get to full-fledged data sets in their own right. So if you are training a number of these models on these different, let's say you take a decision tree, right? If you're training different decision trees for different bags and overfitting, training them to the point of overfitting, the idea is that these bags will in general be a bit different, not too different, but they will in general be a bit different. So sometimes, one bag might have more of certain kinds of data points. One bag might have more of some other kind of data points. Let's say a data set of, I don't know, to give a lighthearted example, let's say it's a data set of, cats, dogs, and rabbits. So it might end up that, some data set, some bag has more pictures of cats, some has more pictures of dogs, some has more pictures of rabbits. In one, the cats look maybe more of Persian cats. In other, you have some other, breed of cats. So in general, the data sets will be a bit different. And if you're training a decision tree to the point of overfitting, that means that that decision tree, it won't perform very well on all kinds of data points that come in. So it won't perform well on cats, dogs, and rabbits. But if that decision tree is trained on a data set which had more cats, then it has become more specialized. It has more, it has become more specialized in recognizing cats. And so you could think of like an ensemble of these learners as sort of a group of, how to say, a group of diversely specialized. Right? Some decision trees are more specialized towards certain kinds of data points, others are specialized otherwise. And, taken as a whole, some will get wrong for a particular testing data point. Some of these over specialized or overfit learners will get it wrong. But the idea is that most of them, right, more than not, they'll get it right. So that's kind of the conceptual or philosophical idea behind tagging. So it's like a group of these diversely specified learners because tags, they are not very different, but they are kind of different. So the decision trees trained on them, they also turn out to have different specialities, different specializations. And when you average the predictions of diversely specialized, right, then you get a better quality prediction. So decision tree is very good, and this part with the randomly selected features for splitting the node, this is kind of optional. This is actually, a special version of bagging, which we know as random forest. So this part with the randomly selected features for splitting the nodes, this is optional. I mean, you can just have like a normal decision tree with different, let's say, like an unrestricted decision tree. Right? That's the model family. And you have different instance decision trees trained on different bags. Right? One decision tree instance on each bag. So that's fine. That's bagging also. But if you're doing this additional thing where for the decision tree on a bag, right, it is further restricted that it is only allowed to work with a subset of all the features in the data set, right, in constructing its questions. Then it's what we know as random forest. Right? So a forest is a collection of trees. So like a collection of decision trees. So yeah, so B is correct, and mm, likewise C is correct. So C is correct because uh, so this is not as easily explained in words, but basically the model complexity of this k-nearest neighbors, it actually decreases with k, the number of neighbors. In other words, a k nearest neighbors classifier with a smaller k is more complex, has more complex decision boundaries than a k nearest neighbor with a larger k. So in other words, it's we know that model complexity is directly related to this tendency to overfit. You have a data set that you should use a linear regression model for. Instead, you use a polynomial regression, right? The model will overfit. So it's this tendency to overfit, right, of the model is related to the complexity of the model. The more the model complexity, the more the tendency to overfit. So in case of KNN, the model complexity decreases with increase in K. So with increase in K, the decision boundaries are smoother. And you can think of it in the extreme, if K is equal to the number of data points. In a K nearest neighbors classifier, if K is equal to the number of data points, if you are consulting all the data points for this majority voting, which KNN does, then for any test time point, then the prediction becomes the majority label. Right? And the simplest classification prediction that you can think of. Whatever data point comes in, predict the majority label. It's called a dummy classifier. So with KNN, if K is equal to the number of neighbors, it becomes or degenerates to the dummy classifier. So that's like a very simple classifier. So kind of easy to remember that with KNN, with the increase in the number of neighbors, the model complexity decreases. So we want something that will overfit. We want something with complexity, right? Each of the learners, right? We want something with complexity. So we want a KNN with smaller k. So it's B. And any questions? If not, is the concept clear?
So can you again explain why
Yeah,
KNN classifier with a smaller value of K is right
right.
for bagging purpose?
So there is this. Right. So there is. Do you get this extreme example that suppose I'm increasing the value of k in k, okay?
Hmm.
And the extreme is that I set k is equal to the number of data points. So instead of consulting like some number of data points, the classifier is consulting all the data points for this majority vote about the prediction on the test time data. So then the prediction of any test time data point that comes in, right, it becomes the majority label. That's how KNN works, right? So we just reading KNN, K nearest neighbors. So a test time data point comes in. Let's say K is equal to 5, then it's like 5 nearest neighbors. Let's say there are 10,000 data points. So what KNN does is, let's say a test time data point comes in, and let's say K is equal to 5. In this data space, right, it's gonna find the 5 nearest data points. So it's gonna find the 5 data points which are the most similar to this test time data point. And then it's gonna take the majority label among that. So what that means is that let's say I see, the classifier picture for tomato, and the classifier has to decide between whether a tomato is a fruit or a vegetable. And there are, 10,000 pictures of these edible items. Some are fruits and some are vegetables. So, this picture of the tomato that comes in, that can be presented as a data point, as a feature vector. Images can be flattened into vectors always. So what it does is in the data space, it basically, pings or computes the distance of the test time data point with every of the other, 9,000 and 9999 data, approximately all the other data points, right? And then it's going to find the 5 data points which closest to this picture of the tomato. So it's going to find the 5 nearest neighbors of this test time data point, this picture of the tomato that came in. And then let's say among these five nearest neighbors, let's say 3 are labeled as vegetables and 2 are labeled as fruits. Then the prediction for whether a tomato is a vegetable or a fruit will be the majority vote among its nearest neighbors. So it will be that tomato is a vegetable. Tomato, for the purpose of this classifier, tomato is a vegetable. So this is how this k nearest neighbors works. Finds or decides. So there's a computation. There's a distance computation involved. The distance between the test time data point and all of the other data points in the data set, right? That has to be computed. So after this distance computation, it sorts all the training data points according to their distances to find the 5 nearest neighbors, or k nearest neighbors in general. And then it makes the prediction as the majority label among the k nearest neighbors. So that's a quick recap of KNN, how KNN works. Now, sort of the extreme case that I'm trying to use to bring out the concept is that let's say I set k is equal to the number of data points. So there are 10,000 data points. Instead of saying k is equal to 5, I set k is equal to 10,000. So it's going to do the distance computation, but that's kind of redundant because now it's going to consult all the 10,000 data points, right? So, if it works as predicting the majority label among its k neighbors or k nearest neighbors, and I set k equal to the number of data points, the prediction it makes is the majority label in the data set, in the entire data set, not just like some smaller number of neighbors, but the majority label in the entire data set. So that means that whatever the data point comes in, so it's a picture of, let's say the majority label in the data set is a vegetable, let's say. So then whatever the picture, what the data point that comes in, whether that's an apple or banana, pear, cabbage, whatever the data point that comes in, it's going to predict it as the majority label in the data set. It's going to predict it as a vegetable. So when I set k is equal to the number of neighbors, so in conclusion, when I set k equal to the number of neighbors, right, then it becomes the simplest classifier that we can imagine. It becomes a dummy classifier. Whatever the data point comes in, don't even look at the data point, predict the majority label in the training data set. So that is the opposite of complexity. So that's the simplest classifier that we can think of. That's a dummy classifier. So kind of 2 ends of the spectrum. So on one end of the spectrum, if I set k is equal to the number of data points, then it's the simplest classifier that we can think of. It's a dummy classifier. On the other end, if I set k is equal to 1, then sort of short on time, so I can't. There's a visual way of looking at this, but if I set k is equal to 1, then the decision boundaries become very complex. So for a test time data point can land anywhere in the data space, and suppose one test time data point, the one nearest neighbor to it, its one closest string is a vegetable. Suppose you move it just a little bit, just a small change to it, suddenly now it's closest to a fruit. Just a little bit of change. So this is model complexity, right? You change it just a little bit, and suddenly the prediction changes drastically. So if I set k is equal to 1, right, it consults just its one nearest neighbor. One test time data point might have a vegetable as its nearest neighbor. Change it just a little bit, and suddenly it might have a fruit as its nearest neighbor. and the prediction changes. So that intuitively, uh, sound like sort of a very complicated model, a complex, like a complex model. So these are two ends of the spectrum. With k is equal to 1, if the model complexity is maximum, it's very complex, very non-linear decision boundaries. And the other end of the spectrum, if k is equal to the number of neighbors, a number of data points, if k is equal to the total number of data points in the data set, then the prediction for any test time data point, whether it's a tomato or an apple, any test time data point, it becomes the majority label in the data set. Right? So whether it's a tomato or an apple, it will always predict it as a vegetable if the majority label in the data set is a vegetable. And we want a KNN with a smaller k because really for bagging, we want to overfit weak learners, right? As somebody in the comments rightly wrote, that for bagging, bagging is, like collecting a group of differently specialized learners, right? So each learner is like, specialized to the point of overfitting. Right, I'm gonna answer that, but each learner, right, in a bagging situation, it's specialized to the point of overfitting on sort of its domain of expertise, if you could think of it that way. So for that, we want something with model complexity, something that's capable of making complex learning decisions. It's sort of like complex, like learn complex patterns. That's understand by model complexity. The model is capable of learning complex patterns. So linear regression has less model complexity. Polynomial regression has more model complexity. And in a bagging situation, we want individual learners to be capable of learning these complex, to be individually specialized, so that collecting them leads to like a collection of differently specialized learners, and the prediction of the ensemble therefore benefits from it, right? uh, Bhavna is
Yes, sir.
yeah,
Clear, sir. Thank you.
Excuse me, sir.
yeah.
If the answer is only the KNN classifier,
Hmm.
in that case, will it one of the answer or
So it's
without
B and C.
mentioning without mentioning the value of
Yeah.
k, only the KNN classifier, the answer?
This is only this is only asking for like a preferential ordering. It's not asking for like an absolute. So this is asking the between KNN with smaller k and larger k, which is more preferred. It's
Okay.
only asking for like the direction of preference, right?
Actually, in lecture, under that bagging, there is the one statement sir given: SVM and KNN have balanced bias and variance trade-off like that. So that's why, if they didn't mention any the information related to constraints of value k,
Hmm.
so generally that KNN classifier has that balanced trade-off between those bias and variance means, then no need to go for bagging,
Right,
isn't it?
right, right, right. This bias variance trade-off is not essential to this question. Right? So bias variance trade-off is if you had to analyze the what is causing the performance of a model to suffer, if you're doing machine learning in practice perhaps, then this bias variance trade-off provides like a framework of analysis to analyze why the model is not performing so good. Whether it's performing not performing good because of high bias or because of high variance. So accordingly, we can make like perhaps like adjust the hyperparameters of the model or choose a different model family. But this bias variance trade-off is not essential to this question because this trend, right, that the model complexity of KNN, it decreases with increasing K. Right? This we can remember factually. The KNN becomes less complex with more K, like more number of neighbors.
Okay.
So this we can remember this factually. Yeah. Okay. So Kirti, kind of an ill-posed question, I think. Tagging for an underfit dataset. Could you explain what you mean by an underfit dataset? Like we have an underfit model, right, or an underfit learner, but what do you mean by an
Yes,
underfit? Like,
underfit
yeah.
models. Actually, we have the two issues, right? Underfit and overfit models. So these two have introduced for that issues, right? Bagging and boosting.
Right, right. Uh, Better not to, right? So you mean can we use bagging or should we use bagging for an underfit for a model family that underfits the given data set? That's the question,
Yes.
right?
I have a little confusion between overfit and underfit, actually. So that's why I'm
Right.
asking this question.
Acha, so overfitting like acha, so broadly speaking, this underfitting is uh, the data has two components abstractly, the signal and the noise. Underfitting is not learning enough of the signal, and overfitting is learning the signal plus going beyond to learning some noise also. So noise is stuff that we don't want to learn because the noise will confuse the learner. Right? We want we want the model to learn the whole of the signal, right? Not less, not more, the whole of the signal. The consistent trends or patterns or structure in the data, right? Not the uh, what's it called, like superfluous or kind of spurious, sort of the spurious facets of the data. We want to learn the consistent trends or patterns only. So if it's underfit, it hasn't learned enough of the signal, which means that the model complexity is inadequate. So let's say it's a housing market prediction, right? And let's say it's a nonlinear relationship that let's say it the price increases at an increasing rate with the area of the house. Right? So it's not like if a house has double the area, then it has double the price. It has more than double the price. So then this is a case of sort of a perhaps quadratic relationship, not a linear relationship. So the signal is quadratic. If I use a linear regression model without without any feature transformation, just linear regression, then the model will underfit because the signal is quadratic, whereas a linear regression model can only accommodate like so much. It can only learn a linear relationship. So that's
Yes, sir.
underfitting, right? And overfitting is the opposite. The model complexity can accommodate more than the signal that is present in the data. So, it sort of goes beyond to, with that surplus capacity, it goes beyond to learning the sum of the noise also. So, the reverse
Okay.
situation, yeah, reverse situation. Perhaps the trend is linear and I use a polynomial model, then it will overfit. And in terms of this bias and variance, which we have learned in week 11, this underfitting is related to high bias. Uh, Overfitting is related to high variance.
Yes, sir.
Yeah. So
Clear.
yeah, this signal and the noise is easier to understand, but this relationship to bias and variance, uh, perhaps I'll share the slide that I've prepared for it. Please just keep an eye out on Discourse. I have a slide prepared for it, but it's not something that this relationship, it's not something that I can bring out in a couple of minutes. Okay, why underfitting is high, a high bias and overfitting is high variance. It's not something I can bring out in a matter of minutes. So just remember it factually for now. perhaps in the next session.
Yes.
Okay.
So here B and C are the correct options, or the only C?
And see.
Okay.
Yeah. So this is from week 12. So we haven't had a full discussion on week 12, but this ReLU, right? This ReLU is short for, right? This ReLU is short for rectified linear unit. It's a fancy word. If you go on to do the deep learning course in the degree level, you'll learn more about it. But it's what is called a Bayesian function in a neural network. So neural networks have this architecture of neurons, and each neuron has a activation function. So this ReLU is one choice of the activation function in a neural network. Another function that we've learned that is sort of in this family of choices for the activation function in a neural network, that's this sigmoid function, the logistic function, which we have seen in logistic regression. So the sigmoid function is also an activation function, just connecting the dots with something that we've learned already. But the form of the ReLU is essentially max 0, x. So it takes one input. So this ReLU, it's a function. It takes an input x and it outputs 0 or x, whichever is bigger. That's it. Okay? So anything that's non-positive, anything that's negative, right, it will send to 0. And anything that is 0 or positive, it will leave as is. Right? So 3.7 will become 0. It will leave as is 0, 5.2, 7.4, 0. So it's so the ReLU function is max 0, x. So given an input x, right, I could write it on the Jamboard. Please request if you want to do so. But it's kind of a simple idea, right? So it's a function that takes an input x, and the output that it gives, it's 0 if the input is negative, and just the output is the same as the input if the input was 0 or positive, if the input was negative. In other words, negative inputs it sends to 0, non-negative inputs it leaves intact. Right? Just some confirmation, please, that you agree that option 3 is indeed the correct option. We can move on.
Yes, sir. Yes, sir.
Yeah, thanks. Okay. So when I came across this question, I found it kind of not a difficult question, but required at least a moment's thought. So we have gradient descent for linear regression, which is set for 100 iteration with a learning rate of 0.01. So just pointing it out here, the learning rate is the same thing as the step size. Okay. So the training loss is increasing after every iteration. So we could set up this. So when we do machine learning practice, we can set up this curve with matplot. We can plot how the training error or the training loss is changing with every iteration. We can plot it on a curve and see whether it's increasing or decreasing, whether it's increasing at an increasing rate, so that we can make a judgment regarding whether the model training is going as we want. So whether the training loss is decreasing, whether it's conversing. So this is the opposite of what we want. We see that the training loss is increasing after every iteration, whereas the training loss should be converging to a minimum. So that's what model convergence means, right? So the training loss is converging to the minima of the loss function of the loss surface. So among the given reasons, what could be the possible reason for the situation that instead of being as we want it, the training loss is decreasing. The training loss is in fact increasing with every iteration. What could be the possible reason for it among these given reasons? Yeah. Indal, would you like to come forward and share your explanation why?
Yes, sir.
Yeah.
Actually, when we train the model on that thing, so learning rate may, if high, then our error will be increasing after by each iteration. So maybe we need to be decrease that.
Right. But you're saying the learning rate that, so you're restating, right? If the learning rate is high, then uh, that is counterproductive. But why is this? You
Maybe the step size required is like 0.01. Yeah, it's quite lower, but maybe our algorithm not converge because of the error increasing, so our algorithm not converge. Then
right. All right. So let me add to that. That's absolutely the correct option. This learning rate may be too high, and C and D are not quite. I mean, not quite pertinent because you know, when it, kind of it maybe we want a model that considers all the features. So it's kind of not not very helpful to say ki don't use some of the features. So maybe we want a model that considers all of the features. So India therefore immediately it is invalidated. So for some other question, these could be valid options. For example, some question about random forest, this could be valid key. If I wanted in a random forest setup, the trees are the trees in a random forest are still very correlated. What might be the issue? So there, the maybe number of features are sorry. So this should be they should be the opposite of options naturally. And they should be too high and decreasing them. So if the trees in a random forest are still very correlated, right? We want the trees in a random forest to be decorrelated, if you recall. Then we should instruct it to select a smaller subset of features. So the set of features with which each tree in the random forest is constructed, that should be decreased. So in that case, C and D are valid options. And if you wanted to decrease the correlation between the trees in a random forest, D would be the correct option. Number of features too high, try decreasing the number of features. But in this, perhaps we want a model that considers all of the features. So it's kind of not very helpful to say don't use some of the features. That's that's a non-solution. Right? So option will be one of A and B. Why is it option B? So for that, perhaps I'll quickly move to the Jambo. Okay. Right. So in general, right, so the loss function, if I plot it, uh, just say hypothetically that there are two features. My data set has two features. So then gradient descent will be looking for a weight vector in R2. In other words, gradient descent will be looking for some W star that is here on this W1, W2 plane. If I add a third axis for the loss function, and I know that the loss function is a function of W given X and Y. Agree? So if, for example, quickly writing it out, if, for example, it's linear regression, right? So the loss function is equal to summation y minus W transpose X whole square. So we see that it's a function of the labels Y, it's a function of the data points X, the feature vectors, and it's a function of the weight vector W. Agree? Right. So, the X and Y are sort of fixed. So let me, I could just write it as L of W. Because in a given machine learning situation, the data set is kind of fixed. The X and the Y, they're fixed. That's the data set. So if in with these three axes, right, if plot the loss function as a function of the weight vector, then it comes out to be, I am drawing it as U-shaped, but it will come out to be cup-shaped. For linear regression, the loss function is convex, and convex just means cup-shaped or valley-shaped, or cup or valley-shaped, right? But I'm drawing it as Egypt here for obvious reasons. So this is the plot of the loss function as a function of the weight vector. We saw that the loss function is a function of three things, and only three things: the weight vector, the data set X, and the label vector Y. We saw that, right? X and Y are fixed. It's only W that is variable in that function. Okay? So in effect, the loss function is a function of, the only thing that varies in the loss function is the weight vector W. So if I plot the loss function as a function of the weights of the weight vector W, I get this plot, which is called the loss surface. And it's called the loss surface because this is with two features, therefore two weights. This looks like the inner surface of a cup, or the sort of inner surface of a valley. So what gradient descent does is, there's the mathematical iteration rule of gradient descent, but mentally think of gradient descent as sort of a person moving downhill, right, with a fixed step size. Okay. So if the learning rate, so think of the learning rate as a step size. Right? If I write out the gradient descent rule, which is that W t is equal to Wt minus 1 minus eta gradient of the loss function evaluated at Wt minus 1. So this part, that gives the decision in the parameter space. So whether in the parameter space, right? So in the plane, you could think of the movement down the valley. So this is like walking down the valley, right? You could think of going down the valley is kind of horizontal movement, right? Your change, your position with respect to height is changing for sure, but it's also a horizontal movement, right? So decouple the change in height is a decrease in the loss, and the horizontal movement is movement in the parameter space. It's the movement in this space. So this part, the gradient of the loss function evaluated at Wt minus 1, that gives the horizontal direction which the gradient descent should go in. So that says that, it should go in this, so from here, starting from here, it should go in, let's say, this direction and not this direction. Because, in the right direction, the loss function is going down, right? The height is decreasing, the loss is decreasing. In the left direction, the loss is increasing. So the gradient, so this term in the gradient descent iteration rule, right, that gives the horizontal direction in which gradient descent should go in the next iteration. Right? And this step size, this eta says how big of a step. So the gradient gives the direction. The eta gives how big of a step it should take in that direction. So there's a direction and there's like and so a vector has a direction and a due, something like that. So the gradient gives the direction, the step size gives the length, the stride. If you're walking, then how big you're taking. So the stride length, the step size. Okay. Now the next term is that as gradient is converging, right? So maybe I'll redraw this figure. I hope the discussion up to this point, mainly this a lot of related concepts, sort of recapping MLF actually. But this idea of a loss surface, I hope it's clear. This loss surface and gradient descent is kind of like walking downhill, right? Are these two things? Yes. Yes, Bhavna.
No, sorry. Wrongly.
Okay. Is it clear to you?
Yes, clear, sir.
Yeah, right. Right. So I'll redraw the figures. Just recapping, there's a parameters. So W1, W2 parameter space. And if I basically join it, if I plot loss function over this parameter space, I get loss surface. And the sum squared errors loss function in linear regression, each error term, so the loss function linear regression is summation EI square, essentially. Each of these EI terms is convex, right? So each EI square, let's say E1 square, E2 square, each of them individually is convex, right? Each of them individually looks cup-shaped or V-shaped or sort of. All of these are convex. But sum of convex functions is also convex. Therefore, the loss function in linear regression is also convex. Convex just means U-shaped. So this is what the loss surface in linear regression will look like. Now, we saw that the gradient gives the direction. The gradient gives the gradient term in this gradient descent iteration rule. That gives the direction in the parameter space which the algorithm should walk into the direction in the parameter space. Now, consider this observation that suppose W1 it's here. W1 it's here on the loss surface. let's say it's some W7. Sure. So this is W1, this is W7. Actually, even for completeness, this is like W1 L of W1. This is W1 L of W1. This is W7 L of W7. Just for the sake of like notational grammaticality. The slope, the gradient at W1 and the gradient at W7. So we can see observation that W7 is closer to the ultimate solution algorithm. Okay? W7 is closer to convergence. Now we can see from observation that the slope at W1, it's a lot steeper. The slope at W7 is a lot flatter. Agree? And this,
Yes.
right? And this will be the case whenever the loss function is convex. As gradient descent comes closer to convergence, the gradient becomes closer and closer. So at the bottom, and that's how we solve optimization problems, right? The gradient rule for optimization problems, if I want to minimize f, then set gradient of f is equal to 0. So at the bottom, at the solution, the gradient is 0. Tangent line is flat. Right? Now this has an indication for gradient descent. We saw that the gradient term and gradient in the gradient descent iteration rule, the gradient term gives the direction. It gives the direction in which the algorithm should go in the parameter space. As the algorithm comes closer to convergence, the gradient becomes smaller and smaller. In other words, the gradient part becomes more conservative. The step size is constant. Step size eta is still constant. But the gradient step, just the gradient part becomes smaller. Right? It becomes essentially a case of diminishing returns. Right? As you come closer to convergence, uh, the signal or the feedback from the loss function, right, it diminishes in intensity. If you wanted to think about it in those terms. So in other words, and this is why we prefer gradient descent. So when we saw linear regression in MLF, right, we saw that there's actually an analytical formula for the optimal weight. So we could express this W star. I don't remember the formula right now, but it was something like X transpose inverse Y. Not this, but something like that. We saw that there's actually a formula. There's a closed form expression for W star. But we introduced gradient descent saying that we prefer gradient descent. And that's because this closed form solution, it's one shot. Since that we either have W star, the perfect W star, or we have nothing. Whereas gradient descent is additive, it is incrementally additive, in the sense that it's easier when I get to like 80% good enough happens very fast. So it happens in this part. So getting to 80% good enough, getting to W7 happens very fast because the gradient up to W7 is very steep. Past W7, and as the algorithm gets closer and closer to the solution, the global minimum, it becomes flatter and flatter, and the algorithm, the iteration updates become slower and slower. When W50 will be very marginally different from W51, right? So we do early stopping. Save on time. This is good enough. Okay. So it's this thing that as the algorithm or as going towards the bottom of the loss function, going towards the global minima, the gradient decreases. In other words, the tangent lines become flatter. The gradient signal diminishes. Right? This was sort of the second part that was needed. And the third and final thing, why, so this question kind of jumped between a number of topics here. So just looking at the question again. So here we saw the loss surface. So the loss surface, if it's a linear regression loss function, then it is convex. No doubt about that. Then, instead of gradient descent going to, instead of gradient descent coming closer into the global minima, like the bottom of the valley we saw, it's doing the opposite thing. So it's that gradient descent is shooting out of the valley, right? And shoot more and more out of the valley. So what might be a reason that? So this almost at the end of it, this longer than I expected. But kind of an interesting question, like I said, connects a lot of these fundamental concepts. This loss surface and this basically the gradient becoming flatter. Right? So those were the two concepts leading up to this. So this is the loss surface. And the idea is this, that suppose it's here. Suppose this is some W4. We are plotting it visually, but I just want to re-emphasize that the main movement is the movement which gradient descent does. It's in the parameter space. So the movement here, the movement is in this plane, and we can plot it on in this 3Ds to simultaneously visualize how movement in the parameter space corresponds with increase or decrease of the loss function. Right? But the movement is in the parameter space. Just wanted to emphasize that. Now, suppose it's at W4. It gets some. So the gradient. So the negative of the gradient of the loss function evaluated at W4. This is direction it should go in. So suppose in the parameter space, so let me plot it here actually. Suppose parameter space, this direction, the gradient of the loss function evaluated at W4. This direction is this direction, let's say. And gradient descent will take eta number of steps in this direction. Let's say eta is some number such that the total step it takes in this iteration is this. So the entire movement x is this. Or maybe bigger. So that the point is. So it has ended up here. So this is this was W4. This was W4. So this is now W5. Look at where it has ended on the loss function. In other words, the direction signal from the loss function, from the gradient of the function, that was well and good. it should in fact have gone in this direction. That was well and good to reach the minima. The minima is here. It should have actually gone right. Well and good. But step size is too big. The way to put in word, the way this is put in words is that it overshoots the minimum. And if the step size is too big, it overshoots the minimum, right? And it actually ends up at W5, where it has overshot the minimum and actually gone to like the opposite side.
So, sir, it oscillates between W4 and W5.
Huh. But there's a catch here. Absolutely, it oscillates, but the catch is that if the step size is too big at W5, so the gradient here was this. The gradient at W5 is even steeper. Right? So what that means is that with a constant step size, okay, let's say it's still taking 5 steps, that's eta is 5. With a constant step size, this means that the move from W5 to W6, it will be even more pronounced. So it overshot the minimum with, like the gradient at W4, which was steep, but still not so steep. It overshot to W5. And at W5, the gradient is even steeper. So it will overshoot the minima even more in the next iteration. And so it will end up somewhere here. So this will be 6. And the loss is even more increased. And now the gradient is even steeper. So it will overshoot the minima even more. It will reach W7 where the loss is even higher. Right? So this is also this kind of, if you have to visualize it. And this is a forced oscillation. Right? Whereas we might be, so some versions of gradient descent, they oscillate, but they have what is called a damped oscillation. So the oscillation is like, one second, something like this. So this is a forced oscillation, where the oscillation is increasing basically, and the magnitude or the amplitude of the oscillation is increasing. We'd be okay with a damped oscillation. Forced oscillation, with the forced oscillation, which is what we see here, the algorithm won't converge. And therefore the answer. And just as a passing note, this is why in machine learning in practice, right, the step size is generally not taken to be constant. The step size is taken to be decaying by some scheme. That's not important. But basically, the step size becomes more and more conservative as the algorithm progresses, as the iteration number increases. Okay. So I hope so far it's been clear.
Yes, sir. Yes, it's clear.
So it's this is the answer. All right. I think we've just some number of topics so far. Let's take a 2-minute break. The interim, if you have any questions, if you through PYQs and I can discuss any questions that you're difficulty with, please drop them in the comment.
So C and D are similar option.
That is actually my mistake. So this should be the opposite of C. Yeah.
Okay.
Okay. Let's take a 2-minute break.
Hello, sir.
Yes, Ishika.
Sir, not related to the PYQ. I have a doubt related to the activity question. Just I need the background for that.
Activity question for which week?
for week 10?
Just share what concept it about. Maybe there's a PYQ
Yeah,
question related to that.
so basically, so for the objective functions of Lagrangian, we uh, have ways like we check max of alpha. No, first we take for min of w, and then the max of alpha greater than equal to 0, and then the function f of w plus alpha star g of w star.
Hmm.
But then we also have a dual of it, which is max of alpha greater than equal to 0, then min of w, and then the objective function.
Right.
So, sir, like, yeah, there was one of the question where this L of W comma alpha was given, and similar uh, mm, for primal and dual we had to check. But then just wanted to confirm that if we start with primal and when we convert it to dual, do we need to check for the convexity of F and G? Because when we interchange the min and max, it will be equivalent only when the f and g are convex, right? So for such functions, always do we need to check, and then
Right.
only tick the other option where yes, the dual and the primal.
Right. So this is, yeah. Yes. The answer is yes, because this is a topic of strong and weak duality. The primal and the dual, they are exactly equivalent only when actually not only when, but they are guaranteed dual. For example, when the function is convex. In general, it might not be, I'm not sure if it's a necessary and sufficient condition. It is a sufficient condition. If that objective function is same, right? The original objective function plus the constraints, right? Sort of combine into a subjective function. Uh, if that is convex, right, that is sufficient to guarantee strong duality. The primal and the dual are exactly, right? So the solution that you get from the primal and the solution that you get from the dual will exactly be the same. In general, that is not the case. In general, you have weak duality. So you have to look at the specific question to, but yeah, and
So it
without,
is 10.4 question 2.
yeah. Okay,
If you want,
so
I can share this screen.
yeah, can we let us take like a 2 minute breather. We've been rushing through some concepts in this last 1 hour. Let's take a 2 minute breather and we'll start again. Hello. Hi. Ishika, could you share the question reference? The question number.
10.2, question 2.
Yeah.
My mistake, it is 10.4.
Hmm. Huh. So in this case, yeah, you won't. So duality is kind of, sort of, not a very beginner topic. It's at least an intermediate topic in uh, th- this branch of mathematics called convex optimization. Convex optimization is one of those pillars of machine learning, along with differential equations, as we're seeing in the modern day, for sort of furthering machine learning research at a research level. But it's only introductory, sort of introducing us to the terminology and the idea, the preliminary idea in at our level. So we won't be given. I would venture to say that we won't be given general questions. Ki, are these two formulations always equivalent? Now, this particular formulation we have seen. So this is not a general question. This is specific to SVM. So we've seen the optimization formulation for SVM. Right? So here it suffices. You might remember this from memory. We can swap them in the max. But we know that the constraint always should be of less than equal to type. Right? So the constraint in the Lagrangian should always be of less than equal to type. So if this holds, then this part will be less than equal to. And then it works out to be a convex function. Just take it as a fact for now. And this is the norm, the squared norm of a vector, which is convex. It just is convex. And the norm of the norm is a function, right? We saw in maths too. So the function norm or squared norm, squaring doesn't change the convexity. It's always convex. And this is Euclidean norm, right? So let's say the vector W is W1 comma W2. Then the squared norm is W1 square plus W2 square. W1 square is convex. W2 square is convex. Sum of two functions is always convex. So Euclidean norm is always convex.
Yes.
And that's why
So
also
what did
again
you say about graph?
connecting to that earlier thing. Yeah. Oh, so when we are formulating the Lagrangian, so this is what the Lagrangian is for, right? Sort of incorporating the original objective function and the set of constraints into a monolithic objective function that can be optimized unconstrained. It's like a single thing. So there are certain conventions. So that's like a machinery, right? This Lagrange, it's like a machinery. It expects its inputs in a certain format. So one stipulation on this, one stipulation of this format is that when we are when we are incorporating the constraints have to be incorporated in less than equal to form. So the constraints are added as Lagrange multiplier times constraint. So alpha times constraint. Okay. So the constraint always has to be rewritten in less than equal to 0 form. So if W transpose, so looks constraint, right? W transpose X times Yi is greater than equal to 1. That means, the equivalent way of writing that is that 1 minus W transpose X Y is less than equal to 0, right? And we always put the constraint in the Lagrangian in this less than equal to 0 form, right? That's a stipulation or requirement of the method of Lagrange, right? So that all the other results that we have available for the method of Lagrange, this the KKT conditions, right? So that everything works as expected. Yeah. But yeah, your original question, like I said, it's this duality is sort of an intermediate level idea. So we're only getting like a preliminary acquaintance with it for people, let's say, go to research later on. So here we won't be given. I wouldn't suppose that we'll be given like arbitration and checking if the min and the max are equivalent, right? The primal and dual are exactly equivalent. But this is not a general question. This is the specific optimum formulation that we have seen for SVM. In this case, they are exactly equivalent because the Lagrangian is in fact convex. It's a sum of convex functions.
Okay.
Yeah.
Thank you.
Right. So let's resume with the problems. So there are two data sets here, right? For a binary classification problem, the labels are color coded, red and green. So a couple of keywords here: hard margin SVM with kernel, specifically with a quadratic kernel. So let's look at one by one. Hard margin will only work if the data set is linearly separable, right? Linearly separable with some margin. So hard margin will not work with a data set that is not linearly separable. So as is, without anything else, if I ran hard margin SVM on these two data sets, it wouldn't converge for either of them. So that's one. So the next is what to do then. Right? So we can kernelize. So that's what this kernel is about. And kernel is essentially feature transformation. So that if I have a data set with, so the data set here has two features. So doing a feature transformation means that, let's say my original features were x1 and x2. I create new features using the numbers in the original features, which are x1 square, x2 square, and x1, x2, x1 into x2. So I look at the feature values for x1, I look at the feature values for x2. I create these new features, and so I get a new kind of data set, like a augmented or modified data set. And this is the essence of kernelization. This modified data set I pass to SVM as is. So this is the kernel part. So kernel SVM is not actually very different from normal SVM. Right? The SVM part is the same. The SVM, the black box, that stays the same. But it's this pre-processing step sort of. Right? This format in which the black box SVM is expecting the inputs, right? I sort of trick it. Right? So I modify the original data set to get like a different sort of data set. And then I run normal black box SVM on this modified data set with these additional features. Now I know how I created those features. I know that I created this third feature by squaring the first feature. I know that the third feature is x1 square actually, but SVM doesn't know that. To SVM, it's just f3, right? And x square is just f4, the fourth feature, and x1, x2 is just f5. SVM doesn't know how those features are related. So SVM tries to do a fit in R5. SVM tries to do a fit in a higher dimensional space. Right? There are 5 features now, so it's R5. And not showing it here because this has been talked about before, but in this higher dimensional space, this data is linearly separable. So how? Notice that the curves, the non-linearity in these two data sets, right? This requires school level coordinate geometry. It's not too much though. The non-linearity in these data sets, they are quadratic. So the first one is a circle. The second one is a parabola. And these are quadratic non-linearities. These aren't cubic or ternary non-linearities. So if it's a quadratic non-linearity, then adding these quadratic features, right, towards using a quadratic kernel will be quite enough to ensure that in that higher dimensional space, right, in that transformed feature space, the data points are in fact linearly separable. And then just run normal hard margin SVM in this higher dimensional space. And it'll work for both. So the answer is that both dataset 1 and dataset 2. Right? So three terms: hard margin, kernel, and specifically quadratic kernel. Yeah. Thanks for the confirmation. Yeah. So any doubts? Please feel free to come forward and ask. Otherwise, I'll move to the next question. Yeah. So wait a second. This is. Okay, let's, in the interest of time, let's skip this question. This is missing some important. Yes, Ishika.
Yes, sir. Sir, in the previous question,
Yeah.
can you use some dimensions and tell us about the transform space? Just examples, what will be the dimension of the transform space?
Sure.
Is it
If
n minus 1?
yeah. So in general, if the original data set had D features, and I use a K degree transformation, then the total number of features in the new data set will be K plus D choose D. So again, if there were D features in the original data set, and I do a K degree, I use a K degree kernel. Right? So here quadratic means K is equal to 2. Then total number of features in the transform space, total number of features, not newly introduced features, total number of features will be K plus D choose D. So K plus D choose means C, the combinatorics, the combination that one. So for example, here D is equal to 2, right? And K is equal to 2. So this is 4C2. So number of features is 4C2, which means 4C2 is
6.
yeah, 6, right? So the 6 features are original features were x1 and x2. The new features, as I said, are x1 square, x2 square, x1, x2, and there's one other that I missed. Actually, it should have been R6. Is the dummy feature 1. So it will also introduce the 0th degree term. Right? So the dummy feature 1 is the 0th degree term. So 1 is x to the power 0. Right? X1 and x2, these are the first degree terms. And x1 square, x2 square, these are the second degree terms. Perhaps not obvious as x1 square and x2 square, but x1, x2 is also a second degree term because the powers add up to 2. Okay? So if this, for example, a cubic kernel, right? And I had a term x1 square, x2. that would be a third degree term because the powers x1 square times x2, like x2 to the power 1. So 2 plus 1 is 3. So that would be a third degree term. So with a quadratic, kernelization introduces terms of all degrees up to the degree of the kernel. So it introduces, if it's a quadratic kernel, it will introduce the second degree terms, the x1 square, x2 square, and x1, x2. But it will also introduce the zeroth degree term. In other words, it will introduce this dummy feature, which is this f0, you could call it, which is one across all the data points. Right? And this is what we used when we wanted to allow linear regression to not pass through the origin. When we wanted to allow linear regression to have an intercept, right? We added this feature that was one across all the data points, right? So it's that same thing. But yeah, in general, the formula is k plus d, k plus d c d, or k plus d choose d. Yes, Ishika? Yeah. Sorry, my correction. It should be in R6. Yeah. So the vanilla hard margin SVM, it will fit it in R6, not R5. So this question, let me skip because I'll have to, there's some, oh no, wait, this is the questions.
So in this question,
Yeah.
something is missing.
No, it's not. So it's asking whether, so it's saying k x1, x2 is a valid kernel. It's asking
Before
whether,
K, x1,
yeah,
x2. So
oh no, right? Could
is
you tell
if
me why no?
x1, x2, k, x1, x2 is a valid. This
Huh.
before k, x1, x2, I could not understand.
So it's saying that this new kernel, let's say I have a new kernel, right? K is some function of x1, and let's say it's let's say I don't know, let's say it's x1 square plus x2 square, let's say, and it's saying ki this k I pre-multiplied by whatever x2 is and whatever x1 is, and I get a new function. Let's call it k2. So it's x1 into x2 into whatever the original k was, whatever function the original k was. This new function, is this a valid kernel? This actually has a quick answer, but if anybody would like to try, Bhavana, if you give it a thought.
So, is it yes? Because for K it is valid. So x1 and x2 alone, if we take, that is also a valid kernel. Combining both is a valid kernel.
Achha. Uh, is the answer yes? Let me see. The answer should be no. Achha. Let me let me skip this question from.
Sir, I believe that since the new kernel is in also R space, so therefore it will be a valid one.
The new kernel is also in R space, isn't it? It's
Like,
the codomain is still the real numbers.
K is defined in R cross R, and it is in R, right? So it might turn out that this will be a valid kernel.
No, right? That's not sufficient to guarantee, right? So my reasoning was going like this: that this k, right? Uh, one second.
Sir, for valid kernel, there are some functions, there are some conditions, no, sir?
Right. But there are these Mercer's theorem. This Mercer's theorem which
Yes, sir, some theorem
provides.
is there,
Yeah.
some conditions are there, no, sir?
Yeah. But where I was going wrong, I'm not sure how, but essentially this kernel function. So if I apply the kernel function to a data set, I'll get a kernel matrix. Okay. So it's like the kernel matrix is the ijth entry in the kernel matrix is this kernel function applied to the ith and the data point, ith and the jth data point as the inputs. So it will be k xi comma xj. That will be the ijth entry in the kernel matrix. And a condition for being a valid kernel is that this kernel matrix is positive semi-different. In other words, the kernel matrix has only non-negative eigenvalues. So I'm just uh, uh, yeah, that actually argument is not adequate. Let me, I haven't given this a thought. I'll take this up in the next session. So essentially
So is there
multiplying, yeah,
so the answer is available on it?
no, the answer is available, right? So this is third term of 22, so question 30.
Okay.
The answer
P
is
by
given as
Q.
yes. Yeah,
Okay, the answer is yes, right?
the answer is yes. Yeah. Ishika, could you share your reasoning, how you arrived at yes?
Yeah. So it is given in the first statement that K is a valid kernel. So K of x1 comma x2 is a valid kernel. And x1
Right.
dot x2, that is also a valid kernel if taken as a kernel function. So the dot product of the dot product is a valid kernel. So x1 x2 into k of x1 x2, the combination is also a valid kernel.
Oh, that's a very good
That way I
observation. So you're saying that these are data points in R only, right? So x1, x2 is essentially a
yes.
dot product. And dot product is a kernel. So you're using this as a fact that the product of two valid kernels is a valid kernel.
Yes.
And also, sir, maybe a scalar multiple of kernel is also valid kernel, na?
Right. A non-negative scalar multiple.
Yeah,
Non-negative scalar multiple, right? Because otherwise, so it flips. So the kernel function defines a kernel matrix. If it's a valid kernel function, then the kernel matrix is positive semi-definite. And if you take a negative scalar multiple of the kernel function, then the kernel matrix is affected, right? Yes, agree. Can be shown. I could come up. I haven't thought up of easy examples for this. Like quick. There's some example that's possible with a 4x2 or 3x3 matrix. Easy enough to construct, but in the interest of time and the remaining questions, let's move ahead. But yeah, this Ishika, refer me to where this is. This might be available. Maybe lecture video because I haven't seen the lecture videos in a couple of weeks now. So this product of two kernel functions is a product of two valid kernels is a valid kernel. Could you provide me a reference for this? Whether it's there in one of the lecture videos.
Sir, I just thought of it like that and concluded that yes, it is a valid kernel. And then I cross-checked in ChatGPT, and it is also saying that yes, it is a valid kernel, product of two valid kernels.
Achha. Okay, let's move ahead with that. Okay. let's just pause for a minute. Maybe later. Right. Yeah. Yeah. Absolutely. So there is kind of more rigorous proof of this
Sir,
in
the
this link.
answer is third option.
Yeah.
Yes, sir. Answer is third option.
So let's look at this question. Data points generated. So the labels are generated with some Gaussian noise, and we use two models to fit the data. Yeah, answer is third option. So the first, we see that the signal is ternary. It's a fourth degree. So the signal is ternary, but model one only has capacity for linear. Only has capacity this first degree. So it will underfit.
It will have higher bias.
So it will underfit means that it will have higher bias. Right.
Hmm.
And the model 2 is more complicated, right? More complex.
It is
So
over.
it'll overfit. And therefore, it will have overfit and it will have more variance also.
Yes, sir.
So model 1 will have higher bias, and model 2 is more likely to overfit. This notion of this idea of sort of model having capacity to learn more than just the signal, so it goes beyond learn some of the noise also, which is undesirable. That's what overfitting is. Okay.
Sir, just a quick question. In
Yeah,
overfit models, we
yeah,
use bagging, right?
yes.
And
So
in
if
underfit, we use boosting.
yes, exactly.
Okay.
Yeah, boosting basically corrects bias, right? And bagging reduces variance. So earlier this discussion in the earlier TA session that boosting corrects the bias in the learner by basically tilting and retilting the data set that comes for training to a successive learner. So bias just means tilt, right? So the learner is undesirably tilted towards some prediction outcome. Boosting corrects this by basically counter tilting the data sets that come for the learners down the chain, so that in the aggregate, averaging over or aggregating the predictions of all the learners in the sequence, uh, it's less biased, right? At least the later learners have had their biases corrected because of this counter tilting the data set. And bagging reduces, right? So if the learners have uh, each individual learner is overfitting, right? It means that overfitting means that I mean overfitting is not unambiguously a bad thing. That's like the lesson or the sort of realization from the effectiveness of bagging. Right? The overfitting means that if that single model had to do, if it had to perform on all kinds of rates, then it's suboptimal. But if it's allowed to be like individually specialized to certain kinds of data points, right? So one learner is specialized to one kind of data points, and others are specialized otherwise, like differently. Then in the ensemble, it's kind of assured that uh, how to say, the majority will be correct. More will be correct more often than not. So that kind of reduces the variance in the sense that variance is model sensitive. Variance is model sensitivity in the sense of this learning, like essentially like different prediction models arising from slightly different data sets. So for example, this KNN example that we saw, the data point for vegetable just shifting it slightly, suddenly it becomes predicted as a fruit. Model sensitivity. So high variance means that the model is very sensitive, and that's model is sensitive. In other words, the model changes drastically with a slight change in the data. That's because of a very complex model learning the noise in the dataset also. It's the noise that varies from dataset instantiation to the next. So bagging reduces this because essentially like essentially that they differently specialize. So more often than not, the it cancels out. Anyway, yeah, we have had a discussion on bagging, so now it's fine. It's fine. So consider a neural network with 10 inputs and 2 outputs. So there are 5 hidden layers, each with 5 neurons. How many parameters need to be learned if there is a bias associated with each neuron in the hidden and output layers? Let me see. Example. So this is saying that it has 5 layers, 5 hidden layers. 5 hidden layers, each with 5 neurons and 10 inputs, 2 outputs. So this is, so to draw schematically, this is R10. This is the input layer. I'm going to draw the 5 neurons. And it's saying that there is a bias associated with each neuron in the hidden and output layer. So there are 2 outputs. There are 2 outputs here. This is what the architecture looks like. So just quickly recapping, right? So this quickly discussing key 187. Yeah. Let me check the answer. Yeah. Okay. So I don't have a formula for this ready. Whenever I have to do these calculations,
Sir,
I draw it. Yeah.
sir,
Vijay?
neutrons means nodes, no, sir?
A neuron. Yes, neurons means
Neuron
the,
means nodes, no, sir?
yeah,
That
yeah.
round you have put. That is,
Yes, yes.
yes.
When the nodes above this. So this is the input layer. These are the hidden layers. Right? So this is the input layer. These are the hidden layers, and this is the output layer. Okay? And all these are neurons. So so the input, right? Each neuron takes all the nodes in the previous layer as input. So what that means is that, let's say this neuron will take inputs from all three input nodes.
So 3 or 10? 10.
What's that? Sorry. R3.
So
Oh,
number of
no. So I drew only three like input nodes here, but it's given that it has 10 input nodes. And the data points have 10 features. The data points which come in, they have 10 features. So yeah, so each neuron takes all the previous the values or the outputs. And let me use the word outputs. So the outputs of all the nodes in the previous layer as input. So let's say this is the 1/1th node, first hidden layer, first neuron. So it takes inputs from all 10. So all of And this pattern repeats even inside the hidden layer, where, for example, this is the 4/2th neuron. So the 4/2th neuron will take inputs from all, the outputs of all the neurons in the previous layer as its inputs or as its input.
So that means we can take 5 into 10 now, sir. First one, 5 into 10. 50 inside coming to the nodes. They are all biases. Bias.
There are some biases, right? So
The second one will be 5 into 5 into, sir. Second layer, from first layer to second layer.
yeah.
Then second layer
So
to the third layer, 5 into 5. Like that.
Yeah. So the main difficulty of the order of presentation. Anyway, so this, I hope it's clear. The node in either the hidden layer or the output layer, any of these neurons, right? They take all the outputs in they take all the outputs from the previous layer as its input, right? So I drew this for the 4/2th neuron, but it's the same with the 4/1th neuron. It takes all the the 5 outputs from all the 5 neurons in the previous layer as its input. Right? So now let's look at a neuron. So a neuron takes some number of inputs. Let's say the input is whatever input it takes. Right? We saw that a hidden layer neuron takes input. So the 4/2th neuron takes previous layer outputs as input. The first layer neurons take the original data point as input, but all the neurons take some input. Let's say the input is in RD. So what happens inside a neuron? So what happens inside a neuron is that let's say this is X belongs to RD. It's the vector of outputs from the previous layer. Whether that previous layer was a hidden layer or whether it was the original data point, that actually doesn't matter. So let's say X belongs to RD. What happens inside the neuron is that this X becomes transformed to W transpose X. And if this is the ijth neuron, then this vector is specific to this neuron. So this ijth neuron has its own weight vector associated with it. So that's the first transformation that happens. Then this W transpose X or Wij transpose X. This is what is happening inside the some general neuron, the ijth neuron. So this W transpose X comes transformed to W transpose X for W transpose Ij, Wij transpose X plus Bij.
Sir, I think, sir,
Yeah.
it takes place, activation function will come, sir. Something
Yes.
will come
Yes.
and give the
Exactly.
output.
Exactly. So now that we have actually drawn this in the previous diagram, we'll just draw it like this. So the lower half of the neuron, it takes this X belongs to RD as input. First, it does this linear transformation. So this transformation, it's a linear transformation. So X is mapped to W transpose X plus B. It's a linear transformation, right? W transpose X plus B. And what is here is an activation function generally denoted by, actually, I don't know if generally denoted, this sigmoid function, I think was the earliest, or logistic function, which you've seen in logistic regression. It was the earliest, or one of the earliest activation functions used for this as an activation function in neural networks. So X becomes X is mapped to W transpose X plus B, right? And then W transpose X plus B is further mapped. Yeah.
Sir, I think for linear data function,
Yeah.
ReLU is used. For other non-linear sigmoid is used. I think, sir.
No, not quite, not quite. So, so this, the purpose of this activation function, the purpose of the activation function is to introduce nonlinearity. So in this preceding diagram, like, if all the neurons, so we saw that a neuron takes an input, gives out an output, and the next layer of neurons takes that output as its input, gives out an output, passes it on to the next layer of neurons, and so on. Each neuron does a transformation, right, from input to output and passes it on to the next layer of neurons. Now the question is, or the proposition is, that if all that happened inside a neuron was a linear transmission, right, it can be shown algebraically. It's not too hard to see that the sum total of, if you think of a neural network as a black box transformation, right, it takes an input and gives out an output. So in this, it takes an input in R10 and gives out an output in R2. Right? So it's like a mapping from R10 to R2. We've seen that in Maths 2. We've seen that in MLS, right? If a neural network did was a linear transformation inside the neurons, then the neural network would be no different from what we have seen in MLS. The entire thing, it can be shown algebraically that if all a neuron did was a linear transformation, right, inside it, then the entire neural network be collapsed into a single linear transformation between vector spaces, like a single matrix, which we've seen since Maths 2. Like nothing new about it. So the reason, the main differentiator of neural networks, like why neural networks seem to have this capacity for nonlinearity, working with nonlinearity, is that the transformation inside, right, the transformation inside a neuron, it has this activation function which is mandatorily nonlinear, and that's it. The active function cannot be a linear transformation. Other than that, it can be just about anything. What it should be has some considerations, but this logistic function is nonlinear. So the sigmoid function, it looks like this, something like this. Nonlinear, right? Lu looks like this. Piecewise linear, but globally nonlinear. Piecewise linear. So this piece is linear and this piece is linear, but ReLU globally is nonlinear. So the only restriction or the only requirement for the activation function inside neuron, which is the main differentiator of neural networks from everything that we've seen so far, everything that we've seen since maths 2, this linear transformation between vector spaces, right? It's the fact that each neuron has this nonlinear activation function on top of it, right? And that's what gives neural networks their capabilities. Essentially, that's like the main differentiator. It's this introduction of nonlinearity, okay? And the weights. What then happens is that linear regression also is learning with gradient descent. Linear regression is also a black box with some parameters floating inside it. So these parameter updates are also guided by gradient descent, same as linear regression. It's also a black box with some parameters inside it, right? But introducing this linearity, right? This non what happens is that these parameter updates now have to sort of work around this nonlinearity. So gradient descent with how to say gradient descent with linear regression is just a single derivative. Gradient descent with a fat architecture like this, that's given a fancy name. It's called back propagation. It's because the feedback from the loss function propagates backwards through the layers, right? Sort of like a I don't know, fluid sort of seeping in, something like that. It's called back propagation. But the parameter update, it's fundamentally gradient descent. Right? And the reason this works is that with the introduction of nonlinearity, this gradient descent, the parameter updates now have to work around this nonlinearity. Okay? So it's a, if you can imagine what I'm saying, like introducing the linearity suddenly places a new kind of demand on the parameter updates. So it has to update knowing that there's a nonlinear transformation upcoming. So that's what gives this neural network. That's the main requirement for in a neural network. The activation function has to be nonlinear. But between nonlinear activation functions, there's sigmoid, there's ReLU, there's modifications of ReLU. Now, the only difference between sigmoid and ReLU, the major difference is that ReLU is a lot less computationally intensive. The idea is that originally people use sigmoid. Then they realized, wait, it only has to be nonlinear. So we can use anything that's nonlinear. Then why use this almost absurdly simple nonlinear function? And it turns out it works. And that's about it. So I think that's quite remarkable. And there are modifications to ReLU. There's some other, there's I think damped ReLU. There are some other versions of ReLU, just as there are other versions of gradient descent. But fundamentally, ReLU is just like a substitute for sigmoid, which is less computationally intensive, just works. And there is also some, in conclusion, there is still some element of hyperparameter tuning. For some data sets, sigmoid activation function works better than ReLU. One activation function works better than another, but ReLU seems to work remarkably well in general, right? And more times than not. So yeah, that's like a quick recap of this neural network. Okay. Yes, Vijay, does that clarify your doubt regarding this difference between ReLU and sigmoid? So in total, the this transformation, right, inside a neuron, it's X. So a data point X belongs to RD. Okay. It is passed on, the output that it passes on to the next layer of neurons is sigmoid of W transpose X. So Wij transpose X plus Bij. Yes. So now we can come back to the mission. Notably, every neuron has a Wij associated with it, inside it, and it has a Bij associated inside it. So it means that there are 27 neurons. So there are 25 hidden layer neurons and 2 output layer neurons. The output layer neurons are still neurons, by the way. So that's 27 neurons. 27 neurons. I try to do it by hand. This would take a bit of time. Okay, so let's do it in shorthand.
So I did, sir, in this manner. We
Yeah.
take each input to each hidden neuron. It's a 10 input.
Yeah.
It
So
is
there will
to
be 5
into 5
weight vectors in R10 and 5 bias
5
terms, right?
bias terms.
Right. Likewise, there will be 5 weight vectors in R5, 5 bias terms. And it's going to be the same for all these.
In last output, 5 into R2 plus 2.
That's one. So we stopped here. So this one then has 5 times R5 plus 5. And the output layer,
Each neuron to give 1 5 into R2 plus
no,
2.
this will be 5 into R5 plus 2, right? So the last layer, the lower half of the output layer, that takes vectors in R5 as input, right? So it will be 2 times.
So, sir, each hidden, each hidden layer
Yeah.
goes to one output layer. So, the 5 to
Yeah.
each.
So it's like, so each neuron in the output layer takes the vector in R5 as input, right?
So it's 5 into 2.
No, it's 2 into R5. Right?
Okay.
If each neuron is taking a vector in R5 as input, right? The output from the previous layer, which has neurons, right? So then each neuron has a weight vector in R5. 2 neurons, so that's 2 into R5, right? Yes? Yeah.
Yes.
Okay, let's
Plus 2 bias.
yeah, plus 2 bias. I wrote it here. It's not. That's it, right? Okay, so let's run the calculation. This is okay. So I'm copying it over from slide 6. So you'll see it frozen on slide 6. I'm working on slide 8 though. So this is 50 plus 5. 50 plus 5 plus. This is overshooting.
Sir, what we are trying to find, sir?
Yeah, let me just finish the question again.
Number of biases, sir?
Yeah.
Number of parameters.
Yeah.
Number of parameters. Thanks, ma'am. Sir, if 3 edges comes to a hidden one neuron in the hidden layer. Only one
Yeah.
bias, no, sir, or three bias.
Only one bias.
Only one bias.
One bias.
So
Only one bias per neuron. Yeah. Yes, Ajay? It was me. Not quite sure. What is the answer? The answer is indeed 187.
187. Yes. Yes, sir, 187.
Mm, Acha, so let me look at this. Oh, oh, I think it's matching up. Yeah. Okay. So, yeah. So there are 6 layers, right? So this will be. So the first layer has 5 into R10 plus 5. So that's 50 plus 5. And there are 4 remaining layers which will have this 5 into R5 plus 5. So this will be 30 times 4. Plus, it's kind of very cramped diagram here. So it's the last output layer will have 2 times R5 plus 2. So 2 times R5, R10 plus 2.
what is
That's
that
it.
50 plus 5, sir?
So 50 plus 5 is 5 times R10 plus 5. 3 times 4 is 4 times. So this will be 4 times R5 plus 5. Yeah. Sorry. 5 times R5 plus 5.
Sir,
So this is 30 or 25 plus 5. Let me write it quick. And this is 2 times R5 plus 2. So these are the W's. So there are the W's, and these are the biases. I think the math works out. So it's 55.
Yes, sir, it worked out.
There are 4 of these. Hmm. So that's 55 plus 120. So that's 175 plus 12, 187. So you know, the main lesson from this uncomfortable exercise of the past 20 minutes is that if you're given a similar question on the exam, please feel free to draw this diagram spaciously.
Excuse me, sir.
Yeah.
Suppose if the particular neuron 4, comma 2, how many
Yeah.
parameters are responsible to reach the output? That's all like that. That was one question.
So you're seeing the 4, how many parameters? The 4 comma 2 neuron.
To the
Uh,
output. Yes.
right. How many parameters are contained inside the 4,2 neuron, right? So to the output, perhaps you mean maybe will be updated with respect to the loss function. So 4,2 neuron has so it takes inputs from 5 neurons, right? So the previous layer has 5 neurons. So it has a weight vector in R5, and it has a bias. So that's bias is like a constant, it's a scalar. So it has a weight vector in R5, so that's 5 parameters, and the bias, which is a scalar, so that's 1. So 5 plus 1, 6. With this diagram, right? So this neuron has, so contained inside it, it has Wij belonging to Rd, right? D is whatever the dimension of the input that it's taking. This 4,2 neuron is taking input in R5. There are 5 neurons in the previous layer. It's taking input in R5. And second is the bias, Bij. And this is just a real number. So in general, like D plus 1 parameters inside it. Is that okay?
Okay.
Yeah. Okay. Yes, Logan?
Yeah, I also have a doubt about the question.
Sure.
I
Which
shared that
question?
I've shared that on the chat, GChat.
The G check? Oh,
Yes,
sure. Yeah.
G space.
Hmm. Okay. Sure. Let's take this question.
Actually, I was trying, and I need to confirm two things.
Hmm.
Uh, since the green one was our prior,
Yeah.
the blue is the posterior, and the posterior is indicating that uh, the failure rate is high, right?
So let me
So,
screenshot the question so that it's there for reference.
so that oh,
Yeah.
I was seeing on my screen actually. Yeah.
Yeah. Yeah.
So how I was approaching this is that, as we can see the graph, the blue one is the posterior one,
Hmm.
and it is indicating that the failure rate is high, as it is more the mass more concentrated towards that zero portion up peak, which is
Right.
indicating high failure rate, equivalently low success rate.
Correct.
And the question is asking about, among the options, which one, uh, like if one is the one is success, right? In success and failure Bernoulli, so one
Yeah.
is the success, so among which one, which will be the appropriate one among the following, and the options were 1, 3, 5. So among them, the least number of ones was 1.
Yeah.
So in that way, we have to go with 1 indicating the least success rate. Is it?
Absolutely. Very precisely correct reasoning. Yeah. So if the yeah. So so once again, like repeating for the benefit of others. Absolutely. The going from the prior to the posterior. If the estimation of the probability, we see that the going from the prior distribution to the posterior distribution is also going from the prior mean to the posterior mean, right? So posterior mean is sort of like a representative or average or expected value of that distribution. So if the posterior estimation of the probability of success went down, so I had a prior and probability of success was about zero point 0.5, and then some data set came in, and then the probability of success drastically fell off, then that means that there were more failures in the data set than successes for starters. So more precisely, it means that, if, for example, the prior predicted 0.5, zero point 0.5. In other words, the prior predicted that the data set that comes in, it should have around 50% successes, 50% failures.
Sir, what
If
is alpha beta of that? Sir?
so, the
Prior.
alpha and beta are the. So where are you seeing this alpha and beta?
No, no, so it's a beta distribution. It is written somewhere else. I saw.
So the beta distribution is just a
Okay.
probability distribution over the unit interval support, right?
Bayesian estimation posterior.
Yeah. So
Beta distribution is given there, sir, with
yeah,
P describes a parameter and
yeah. Actually, the fact that this is for a beta distribution is actually not very important for this question. And the beta distribution is used because and a beta distribution is used to model the probability of success, because beta distribution has support for unit interval. And probabilities are like that, right? So beta distribution is defined over the interval 0 to 1, and that's probabilities are also between 0 and 1. So that's why beta distributions have application power for modeling probabilities. But it's not actually very important here. So here, what's important is that the prior has a certain peak. Right? That's mode actually. I said it was the mean, but it's actually the mode. The most likely, uh, right? So the prior has mode zero point 0.5. The posterior has mode a lot less than 0.5. It means that the uh, sort of more easy, put in more easier terms, it just means that the the prior distribution places some estimate or some value or some number on the most likely value of the probability of success. Let's put it that way. The prior distribution gives some number to the most likely value of the probability of success. Same with the posterior distribution. And the most likely value of the probability of success down. It means that the data set that we saw in between, going from the prior to the posterior, there weren't as many data points, there weren't as many successes in that data set as was predicted by the prior. So the prior was predicting 50-50, 50% successes, 50% failures. And the data set that came in had fewer than 50% successes. In other words, more than 50% failures. So naturally, probability of success will go down. But here, the probability of success went down drastically. So from 0.5, it has gone to like 0.2 almost. So that suggests that uh, like very few successes were seen. Right? Perhaps no successes were seen, and only the data set only had failures. We
sir,
only saw
when it
failures in the
falls
data set.
below point, sir, when it
So,
falls
sir,
below
once
point five,
indicate
Yeah.
the success, right?
What's that?
Once indicate the success,
Success.
like number of
Yeah, yeah,
success.
yeah, yeah, yeah.
Okay, okay, okay.
One small thing, sir, to confirm in between. So,
Yeah.
as can we comment on the peak? Like, since if we had the peak, if we had the same posterior as the
Yeah.
prior, but only with the high peak, so that indicates confidence that we are now more confident that we were absolutely right.
And very good question. If the prior, I don't think it's possible that the posterior will really exactly the same prior, but what you're saying is that the posterior has the same mean as the prior, right?
Means same mean but with high peak.
Yes. It means that the data set has just reaffirmed or like reconfirmed the prior belief.
Okay, and
Yeah.
if we'll have same thing but same mean, but suppose if we have some pressed or
Yeah.
expanded one, then it will show some less confidence that yes,
Hmm.
you were correct, but we are less confident, something like that, with low peak than the prior. Can we have situations where we will have the low peak than the prior, but the probability will be on 0.5?
Good question. I'll have to think about that. So that actually, this peaked is the fourth moment, right? So the peakedness of a distribution is the fourth moment, the kurtosis. So I'll actually have to look up the formula for, this is what I would do if I were interested. Look up the formula for the kurtosis, the fourth moment of this beta distribution, and draw some inferences from that.
Okay, and one more
Yeah.
small thing regarding that alpha and beta, those arguments.
Yeah.
So, can you just brief in short that how those two arguments impacts the structure of the graph you are taking? Like one must be controlling the skewness, one must be controlling the the
Right.
peakness.
Yeah.
So, if you could brief in short.
Uh, One second. Just give me a minute. Let me look up my material. Let me show you. One second.
Mm.
Right. So moving to the Django.
Sir, the mean of the posterior is less than 0.5, no, sir. It should be 0, no, sir.
Yes. In this question, the question that Aladdin has shared, the mean of the posterior is closer to zero. It's still not zero. Something
Less than 0.5, no, sir. What are
less
if the
than
mean
yeah,
is less than 0.5?
yeah, less than around 0.2.
Yes, sir. That means it is a 0, no, sir. Result.
What is zero?
The label should be considered 0, no, sir.
Uh, the label of one second.
Result. Classifier only, sir. This is only 0 or 1. If it is more than 0.5, it should be 1. So it seems
No, no. So this is uh,
I don't know, so I'm just making a statement. If it is more than 5.5,
So if this Bayesian estimation was for a classification setup, it need not be. It might just be a modeling, like a theoretical modeling exercise. But if this Bayesian estimation was for a classification setup, we've seen, for example, this naive Bayes. Right? So then the one, right, the 0 and the 1, the probability on the probability axis, the
yes,
corresponds to the probability that it belongs to or should be assigned to the positive class. And if the posterior if the posterior is less than
because of
0.5, yeah,
because of adding the data, the mean has come down, sir. Here,
yeah.
so it should be 0, no, sir. I'm just saying. I do not know. Maybe Mohammed
I
sir
mean,
answered.
but once again, one second. No, you're absolutely a very good question. You're saying, so let's say the posterior. The prior is, let's say, probability of span. The posterior is probability of span given X. That's what the prior and posterior is. Just some is like one example that you've seen before. The prior is probability of spam, the general probability of emails being spam, and the posterior is probability of spam given X. So the probability that, after I see a specific email, is X, right? What is the probability that X is a spam? Probability of given X, right? So this posterior and prior, that's it. But in general, probability of spam given X and probability of not spam given A don't add up to 1, right? We have seen this in naive ways that they're coming from two different generators. So it's not like probability, like the spam class is one generator, the non-spam class is another generator. Right? So the probability that an email came from the spam class is like, to put it in another way, the probability of the spam class reading this email is entirely distinct or disjoint from the probability of the non-spam class generating this email. They are two distinct things, two distinct ideas. You agree, Vijay? Like
Yes, yes.
if there's like two generators, right? They're distinct, they're independent of each other. So their probabilities don't add up to 1 as such. So it might be that in this case, probability of spam given X is zero point 0.2, but it might be that probability of not spam given X is 0.1. Right? So it's still classified as spam. If we are interpreting this Bayesian estimation problem in a naive Bayes generative setup. Yes, Vijay? Yeah. Okay. But Aladdin, does that oh, you asked me for this graph of the beta distribution, right? I don't think that's very important for the example, but I'll just quickly leave it here because
Actually, I found it and I thought that maybe they can do a variation with the peak. So I thought,
yeah.
no, it's uh, one thing, one question was there.
Yeah,
It was
yeah.
uh,
Sir, I can't hear, sir, what he said. Answer is
The one thing that Acha, so the one, let me just ahead, right? So I could share the graphs with you in person, but for the benefit of everybody, two facts I think are very informative to remember, which is that the beta distribution, the beta dis the uniform distribution that we have seen, a uniform distribution in the interval 0, 1 is a special case of the beta distribution with alpha and beta both equal to 1, right? So we know that a beta distribution is conjugate prior. So if my prior was a beta distribution and my data set was a Bernoulli data set, right? Then the posterior will also be a beta distribution. In particular, this means that if my prior was a uniform distribution, in other words, what is called an uninformative prior, right? Like no inclination towards any outcome as such, right? When it's entirely unbiased, uninformative or unbiased prior, right? And some data set is observed, then the prior was a beta distribution. Uniform distribution is a special case of the beta distribution. The posterior will be a distribution also. So this one fact is very, I think, useful to remember, that the uniform distribution or an uninformative prior is a special case of the beta distribution with both alpha and beta equal to 1. Is that, Aladdin, let me leave that here. Let me take up a
Yes.
couple of more questions. You
Sure.
said you had a question you wanted to ask, right? After this.
Should I ask, or if someone?
Please do.
Oh, sorry, actually, my voice was not clear. Should I ask, or if someone has?
No, please do. Please do. I mean, we have another 15-20 minutes. So, yeah, please do.
Okay, okay. In that time's time. Actually, there was a question related something. It was talking about bias, but instructor confirmed that we will not see any questions regarding bias.
Yeah.
So, a few things just to confirm verbally. Uh, like when we have that bias things, so the additional thing we will perform that. Suppose in SVM also we have
Yeah.
our decision boundary passing through the origin. So when it will have a bias or intercept, the decision boundary could pass through cutting the y-axis, right? So if what we do, like if you don't have intercept, any data point which have the like calculated, we have that data sets, and it satisfies that suppose we have a weight in 2D. So the data point will satisfy that na w1 x1 plus w2 x2, so satisfy that the equation. Suppose in SVM, if we have the data point on the boundary,
Yeah.
so it should satisfy that na w1 plus x1 plus w2 plus y1 equals to
Yes,
1.
your
That's boundary.
that thing, right? That W transpose X times Y is greater than equal to 1.
Greater than, yeah. So
Yeah.
for data points lying on the boundary, equals to 1 will satisfied with the weight.
Right. Right.
So in addition, when we have bias, so everything will be same. We will just have W1, W2, and the last term W3 with 1. Like we will add the dummy 1
Right.
to the sample, feature, and it will have corresponding W3, right? So we will carry the process with that W3. Like we will have now D plus 1 uh, features for weight if we have
Right.
intercepts.
Right.
So, then why I was not getting, if I could, I'm sharing the question. Actually, I was
Yeah.
following this concept. Still, I don't know what I was missing. Uh, shared again on the G chat.
Okay.
And one more thing, small thing.
Yeah.
As we talk about the perceptrons, and in perceptrons we have that weight update rule. That so it is like that for WT plus 1 we have WT plus XIYI. So here we haven't introduced uh, the learning rate explicitly, that eta 1 that we had earlier in the gradient descent also.
So let me look at the question first. Training examples with two features.
So can you enlarge this question, sir?
Yes,
Please.
yes.
I can't. My eyes are very narrow. I have
Yes,
less
yes.
eyes.
Yeah. Sorry for the negligence. Is this okay now?
Consider training example
Yeah.
with two.
So in the meanwhile, Aladdin, what's your question about this?
So why exactly, like I was not getting like how to solve. First thing what came into mind, like maybe conceptually where I am lagging, I don't know, like
No,
that
but this
statement,
so
the
the
learning rates.
separator. Yeah.
Mhm.
This,
So that
what is?
statement consider the learning rate to be one. So first thing that where I got stuck
Yeah.
is where comes this learning rate now? Like we haven't introduced
But
any.
we have, right? We have in one of the TS sessions we were talking about. You remember that question where it was a linearly separable data set, but perceptron was oscillating between like an upward sloping and a downward sloping separator. It's
Mhm.
like two X-shaped, two separators sort of oscillating in an X-shaped.
Yeah, the
Uh,
initial weight and the iteration
yeah,
order was the fact were two factors.
right.
Mm-hmm.
But I also said ki it might be because this perceptron update, right? It is overshooting what it should be. So it is, let's say, downward sloping. It's from the third to the second to the fourth quadrant, right? So let's say it's that separator, second
Mm-hmm.
to the fourth quadrant, right? And
Mm-hmm.
it sees a mistake and it overshoots downward sloping, like first to the third quadrant. Whereas the correct separator should be the y-axis itself. In other words, overshooting, right? And
Okay.
perceptron gets stuck. It keeps oscillating because it keeps overshooting. Even when it reverts back, it still overshoots and goes back to its original configuration.
Okay.
Versus if we had introduced a step size, when it does a weight update, right, similar to gradient descent, how much how much it changes the weights, right? That is gradually damped, right?
Now this will make sense. Like instead
Yeah,
of focusing on maybe it is handling in this way. Like instead of focusing on what initial weight you should choose, so
yeah.
rather than that you have an alternative. Just have a factor that at what rate you should fluctuate. So with 0 0 also, with if there we had 0 0 initial weight that was not working, but with a factor eta we can introduce
Hmm.
the factor eta, and it can happen that with 0 0 weight also it will converge.
Exactly.
Hmm.
It will basically damp down to the desired separator or the
Hmm.
correct separator. Yeah.
Okay, right. Okay, so okay, the here his learning rate is 1, so it is not going to create any issue. Everything will remain
Sir,
same.
sir,
Everything is as we have
please,
learned.
please tell me about this question, sir. What they want exactly?
So this
I'm not
to
clear about the question,
yeah,
sir.
this question to is a very standard question on this perceptron update rule, right? So W is equal to W plus XY if X is misclassified. So this
So sir, I was taking 1 and minus 5 as W1, W2 and W3 from that, uh, since the decision boundary was given as x1 plus x2 minus 5 equals to 0.
hmm,
So I was trying to extract the coefficients for the weight vector. So 1 comma 1 comma minus 5 should be the weight, or I'm going
uh,
wrong.
Sir, W0, we have to start with 0 0 now, sir.
right. Just give me 1 second. So
I
let
can't
me let's
understand this.
look at this sentence.
This question
So
I can't understand, sir. Question itself.
Acha, so let me explain the question first.
Yes, sir. Yes, sir.
Yeah. So I don't know. I don't think I can zoom it forward. So this
Consider training
so
samples.
Yes. So there is this data set, and it's a binary classification data set, just 1 and -1 as the labels. So perceptron model is trained on this data. So ith iteration, the decision boundary is given as you're right. Yes, you are right. I think
So at this iteration, we are having the weight 1, 1, and -5. Like if you have the intercept.
your this earlier thing that you mentioned that the data set is augmented with this dummy feature, right? That did happen. Otherwise, this in x1 plus x2 -5 is equal to 0 couldn't the -5 couldn't happen. Yeah.
So
So it's been
when
implicitly been
W,
augmented. Yeah.
W3, so 1, 1 and -5 is our current weight. And since 1, comma 6,
Yeah.
that sample has been misclassified, though, so we are going to update on that point.
Correct.
So basically,
Correct.
it will be our current weight, which is 1, 1 minus 5,
Yeah.
plus that 1, comma 6, comma 1 into -1, the
Correct.
actual level.
Yeah.
How that will lead us to option C, which is -1, -11, and -7.
So wait. So 1 1 -5. Let's see. This 1 1 -5.
Plus -1, -6, -1.
So it's 1 1 minus uh,
So we will minus 1, comma 6 are the two features, and we will introduce that one dummy. So and the label is -1.
yeah.
Oh, for that minus we have introduced. So 1, comma 6, comma 1.
Okay. So this is sorry. Let's go 6.
0, -5, and -6. Yes. So our intercept is coming as that. This one. Yes. And actually, it was like I thought if it is pretty straightforward, then the option was not actually bias.
Uh,
Sir,
okay.
how you got 1 1 minus 5, sir? First tell me, sir. How you got 1 1 minus 5, sir?
That I got because this separating line, right?
Separating line is x1 plus x2 minus 5 equal to 0.
Yeah.
And you
x1
can
plus
see
x2 minus 5 is equal to 0.
Yes, sir.
And this can be written as 1 1 minus 5
Equal to 0, sir.
x1 x2 1.
you have that boundary of the dot product of the weights and features W transpose X greater than or equals to 0.
Right. So essentially this is x1 plus x2 is equal to 5. So it's the downward sloping line. So the separator looks like this.
Yes,
So there
sir.
are
Yes, sir.
some points here. some blue points here. So it's to accommodate for this intercept. This separator does not pass to the origin. So the origin here, separator does not pass to the origin. So to accommodate this,
It goes through -5 now, sir.
so it doesn't go through the origin though, right? So this equation does not satisfy the origin. Okay. When 0, 0 would not satisfy this equation, right? So it would be -5 is equal to 0.
Yes.
Yeah. So the
X1
separator does
plus
not pass
X2
to. Yeah.
X1 plus X2 equal to 5. Okay.
Yeah. So
some value in 3, some value it may be 2.
Yeah. All right. So I think we've been going for 3 hours.
So if like last 2-3 minutes, if we can talk.
Sure. But let me take this question on another day. Let me just look into this a bit.
Sure. I just wanted to confirm the very initial thing that we are going right with the weight vectors, right? 1, 1 and -5.
As far as I understand, yes.
Okay, fine. We can wait this. One more I've shared on your chat, GChat. This will not need too much discussion. Actually, I just
we have discussed this, right? The YW transpose is equal to 0 defines the the hyperplane perpendicular to the weight vector.
So there is not exactly. I don't know why. Okay. Sir, another question I have shared on your chat.
Yeah.
If you could present that fast on the screen so that
Sure.
I just want to confirm 2-3 statements regarding that.
I can see that question in the chat, sir. Chat.
Yeah, this one.
Hello, this is the one.
This one.
Great, sir. Great.
So
we've seen this question a number of times. So standard question.
Just confirming something.
No, go on. Yeah.
So what I was thinking, if you just zoom out so that we can see the whole diagram.
Yeah.
So as we can see that the split has been done on a particular feature. So on the first box, we can see at 50-50, we are going to split on yes and no. So here is the probability that 50-50 of 0.5, 0.5. Suppose we are going to yes, we came up here with a probability of 50-50. Here again, we are having a split. So again, on the remaining 50, we will have 50-50. So going to 0, we are going to 0.5, 0.25, half of 50-50. So
correct.
This is the reason, like for 0, we will have 0.25 probability.
Right. So the data points lie on the unit square. Agree? The data points lie on the unit square. So the only path to 0 is 1/4 of the unit square, right?
So make it bigger, sir. I couldn't see it. Please.
So this is saying that the data points lie on a unit square. This split splits the unit square into half. So it's half of the unit square. Right? Like a vertical half. Right? Not diagonal.
Yes.
So yes, Bhavna. Thanks for attending. I'll see you in the next one.
In the half, and again the second split will again half that.
Again half it. So it's 1/4 of the unit square.
So 0.25. Okay.
Yeah.
And had it been asked for 1, then on the first split, as for 0 we get to 0.25, the same we will have for 1.25, and in the first split on the right hand side for 1 we have 0.5. So 0.75 will be for 1.
Right.
Okay.
Absolutely. Yeah.
So so this is playing the major role that the theta on which we are splitting our nodes.
Yes.
For 0.5 theta, we can see that we were exactly creating a 50-50 scenario. So could have been, if it could have been less than 0.6, then we could have been playing on 0.4 versus 0.6.
Right, right.
Okay, okay. I was just confirming if we could face some variations. Okay, okay.
So
Fine, sir.
Absolutely, absolutely. Yeah. And here
so
it's cleaner. Yes, Vijay.
what is it? What is the example, sir? Is answer is sir is telling what is the example, sir?
So
Yes, yes,
instead of the split thresholds being zero point 0.5 and zero point 0.5, this
yes,
could have
sir.
been, for example, that this is zero point 0.4 and this is zero point 0.6.
We can do it,
Right?
sir.
Can be, can be. So in that case, if this was zero point 0.4, right?
Yes, sir.
So then this would be zero point 0.4 times, so it will be 0.24. So if this was zero point
Fine.
0.4 and this was zero point 0.6, then again it would be like zero point 0.4 into zero point 0.6, so 0.24. So we can think of it in probability kind of product kind of, or we can think of it visually, like how we are breaking up, slicing a unit square,
Yeah, actually, wherever
right?
there comes the probability, I always try to go with that one fundamental thing, that favorable by total. So
Huh.
Sir, but those are two labels, no, sir. Two
No, these
different
are,
two different labels, no, sir.
yeah, you're talking about the 0 or the,
No, no, sir.
the,
X1 and X2, sir. They are X1 and
these
X2.
are, these are features, right? Not labels.
Yes,
They're
yes.
features, right?
Different features, no, sir.
Right. Absolutely. Yeah. These are the thresholds on those features.
Yes, sir.
Yeah. Anyway,
okay, sir.
Alogin,
Mhm.
yeah.
Done, done.
Chalo, ठीक है.
So Vijay, like, did you get this question? Like,
Pardon me, sir.
yeah, you get this question, huh? Like,
No, I can't hear you speak. Can you speak louder, sir? I am very old person. My
okay, okay.
ears are all
Am I?
sensitive.
No, no. Actually, am I audible now?
Now you are audible.
You
Yes.
got this question, no?
Sir,
You have got this question, like this one.
I
And
don't know.
Vijay, he's asking कि this question is understood to you, right? There's no, you understand how this question,
No, sir.
uh,
Still, I have a doubt because
yeah,
X1, X2 are totally different. Two what you call you said attributes or whatever
huh?
parameter
Attributes, yeah,
attributes. Two different. X1
yeah,
is not linked with the X2. So
yeah.
even if it may be 75% of the X1 will be there, and
Uh,
X2 may be less than uh, zero point 0.2 also.
So can I take this in a minute so that
sure,
we.
sure, sure.
So
Yeah,
one thing you can. Hmm.
I'm just
So
giving an example. I don't.
sure, sure. So as we can see in the question, it has been mentioned that your features is going to lie between 0 and 1.
Yeah,
So
0 and 1, and
okay, fine.
X1 will be lying almost all
Half.
are above 50.
Okay, so if you are considering x1 as the x-axis, suppose,
Yes, sir.
so less than 0.5 will split your
Yes, sir.
square of 1 cross 1 into half.
Yes,
Fine. So it will split your square into half. So for going to yes part, you have a probability of 0.5, 50-50 chance. Either you will go to the left split, or either you will go to the right split with a
yes, sir.
50-50
Yes,
chance.
yes,
Why
sir.
50-50 chance? Because it is exactly splitting the two halves in equal areas.
Yes, sir.
That's why 50-50 chance. Again, you can see that when you have encountered a yes with a 50-50 chance, you will again say, suppose x2 is y-axis. Fine. So it is again splitting that two shapes into from the mid.
Yes,
So
sir.
you are going to get four small squares of same area.
Yes, sir.
So initially you went there with 50-50 chance. Again you splitted that again on 50-50 again. That 50 to 50-50 again. So for going to 0, your probability is 0.25. Why 0.25? Initially 50-50, and again 50-50 of that 50.
Yes, sir. Yes, sir. You are right, sir.
So for
But
0, you will have 0.25.
but my probability doesn't fall under that 50. What I can do, sir? Suppose
Uh,
x2 doesn't fall under 50. Only two x2 are 50.
uh, in that sense, in that situation, like suppose we were saying we saw that our area was exactly divided into half. That's why we did half of 50, which is 0.25. But suppose your area get divided in the ratio 0.6, 0.4.
Yes, yes.
Then what you will do, you will calculate your probability in that ratio, that if it is getting divided into zero point 0.6 to 0.4, then you will also calculate your probability in that ratio. Initially when we had 50-50, so 50-50 is half half, so we
Oh, okay.
calculated our probability in that ratio, half half.
Okay,
But
sir.
when you will have 0.6 or 0.4, then you will calculate your probability in that ratio, 0.6 and 0.4.
Fine, sir. Fine, sir. Fine, sir. Excellent. Sir, you tell me the question in which paper, which year these questions are coming, sir? Because
So I'm
I
not
couldn't.
sure actually. Like one of my friend was discussing
And the earlier questions also you asked were very difficult questions, sir. The one you asked, prior and posterior.
that was also asked in one of the group, in MLT group.
What is the answer, sir? You said one, no answer. I am still not convinced, sir.
In that graph, sir, could you please share? Like we can
No, sir.
finish it quickly.
Because
That
okay,
graph photo, that graph picture,
that graph also,
Uh,
sir. Mean
which
is
graph?
less
This
than
question or which graph?
previous
posterior,
one.
prior,
Previous
posterior.
one, mean is less
Yeah,
than
yeah.
0.5, no, sir. Mean is less than 0.5 means it has come down, no, sir. Zero.
So if mean is less than 0.5 means that like more
We have
failures seen than
to.
successes, right?
So you are moving towards zero, right? Closing to
Yes,
Right,
zero.
yes, sir.
right,
But
right,
one
right.
answer you are giving one, sir.
So closing to zero is indicating कि you have very high failure rate,
Yes, I failure. Yes,
which equivalently you can say very low success rate.
yes, yes, yes,
So as you can see in the options, we have been provided with 1, 3 and 5. So what could be the number of ones? So number of ones is indicating success, and we can see in the graph that we will be getting very low success, so
yes,
very low number of ones.
yes, sir.
So from the three options 1, 3 and 5, we can see 1 is the lowest one, so it is most appropriate.
What can you say about the what is written there, sir? What you can say about the number of
Ones, that is
ones?
number of success. In Bernoulli you have na 1 and
Yes,
0
yes, sir.
as
One is the
success and
success,
failure.
zero is the
Yes, so
one
it is
success.
saying most appropriate. We cannot comment directly that yes exactly this will be the number of ones from the graph,
Yes, sir.
but relatively we can comment that we will have very less success.
Where it is written very less ones, sir.
From the graph we concluded, as we can see the blue.
Concluded, sir. But answer where it is given, sir.
Sir, in
What?
the in the C, like tick is green mark tick as one. uh, Below the portion there were more options.
1, 0 and all will be there, no, sir.
There were more options below actually.
Below is 0 also is there, no?
Zero is also there.
Then zero should you should say 0, no? More
No, no,
zeros.
Mane. Then what Vijay is saying that maybe there was, as you're saying, maybe just a single success, but might have been that there was no successes at all.
Yeah.
So maybe, yeah,
Maybe
If
then
there is
maybe,
90% failures
uh,
and 10% success, we always say it's a failure, no, sir.
maybe we could have then decided from the option, like as we can
Ah,
see in the options. So
perhaps, yeah,
one was the least one.
Okay, sir.
exactly, exactly.
Okay,
Good,
sir.
good answer. Thank you.
Hmm.
Thank you. Real
Yeah.
thanks. Okay, sir.
Thank you so
Good.
much, sir.
Good time we had, sir.
Thanks for attending. I mean, yeah, really, as much as these TS sessions, also enjoying these sort of in and around the discussions.
Yes,
All right.
sir.
It's very
Yeah,
difficult to keep pace with youngsters.
yeah.
They are all very intelligent. Thanks.
All right. All right. Now all here to learn, right?
Yes,
Okay.
sir. Let's
All right.
learn.
Let's meet in the next session, and take
Okay,
care
sir.
until then. Yeah.
Thanks.
Bye.
Thank you, sir.
Yes.
Good night.
Thank you, sir. You have
Thank you,
spent
sir.
more time today, sir. Thank you very
Yes,
much.
sir. Thank you so much for your efforts. Like,
Extending more to time.
yes, we will have one last session with you the next